Hello everyone, this is Dr. Amudha, Associate Professor, Department of Science and Humanities Physics, RMD Engineering College. In this video, I am going to talk about semiconductor diode laser. When you see the types of lasers, lasers are being classified into 5 major categories based on the active medium. They are gas laser, and the active medium will be helium neon laser. Okay, helium and neon gases are used as active medium. And in the carbon dioxide laser, CO2 and a mixture of gases are used as an active medium. Next is a solid state laser. Examples are UV laser, NDR laser. So solid type of material will be used as an active medium. Next comes this liquid laser, europium silate laser. So active medium will be a liquid medium. Next is a semiconductor diode laser. Some of the examples are gallium arsenide laser, indium phosphate laser. Semiconductor diode is used as an active medium. Then last comes this dye and the chemical laser. Example is rhodamine G6 laser, where a dye material is used as an active medium. Now we are going to see briefly difference between direct and indirect bandgap semiconductors. Direct and indirect bandgap semiconductors. In some semiconductors like germanium and silicon, most of the energy is released in the form of heat during the recombination process. That is, the electrons combining with the holes, you have the energy will be released. They are called as an indirect bandgap semiconductor. But in the case of other semiconductors like gallium arsenide, indium phosphate, etc., the energy is released in the form of light during the recombination process. That is, when the electrons combines with the holes, you get the energy released in the form of light. In the case of direct bandgap semiconductors. Now, semiconductor lasers are used to generate laser beams. They are very compact in size. When the diode is forward biased by applying the external source to a p-n junction diode of semiconductors, holes are injected from the p-type into n-type and electrons from n-types are injected into p-type. The electrons and holes recombine and energy will be released near the junction region. And the semiconductor laser are classified into Homo junction laser and the HeteroJunction laser. Direct bandgap and indirect bandgap semiconductor. In the case of direct bandgap semiconductor, the minimum of the conduction band and the maximum of the valence band, they will lie in a same k vector, same momentum value. Then the recombination of electrons and holes takes place directly. And during this recombination process, you have the photon will be emitted. Whereas in the case of indirect bandgap semiconductor, the minimum of the conduction band and the maximum of the valence band do not lie in a line, and the electrons and hole recombination takes place through an intermediate region which is called as a traps. And during these recombinations, phonons will be emitted. And in most of this case of semiconductor diode laser, direct bandgap semiconductor is used, which is mostly of the compound type. Now, what is Homo junction laser? Homo junction laser is basically a p-n junction diode, and in this Homo junction laser, the p-n junction diode is formed by a single crystalline material. Since it is a single crystalline material and there is only one junction, it is known as a Homo junction laser. An example is gallium arsenide, indium phosphate, etc. Whereas in heterojunction laser, it is formed by two materials. On either side of p-n junction, you have two different material. Okay, that is p-n junction has one material on one side and a different material on the other side. So it is called as heterojunction laser. Example, it is formed between the gallium arsenide and the gallium aluminum arsenide. Now semiconductor diode laser. Here you have this laser action takes place between a band of energy. So here the conduction band plays the roles of excited level, whereas the valence band play the role of ground level. A population inversion requires the presence of large concentration of electrons and holes in the valence band and the conduction band respectively. A simple way to achieve the population inversion is to make a semiconductor in the form of PN junction diode from a heavily doped P and N type semiconductors. So here the PN junctions, PN and materials are heavily doped. Now let us see in detail about Homo junction semiconductor laser. It is a specially fabricated PN junction device which emits coherent light under forward bias. Now what is the principle? The electron in the conduction band combines with the holes in the valence band and produces energy in the form of light. This photon induces another electron from the conduction band to move to the valence band and stimulate the emission of coherent photons. So as soon as the PN junction diode is formed, okay, and it is forward bias, you have the crossing of charge carriers takes place, and electrons to begin with combines with a hole, produces a photon, and this photon in turn induces more and more recombination, so that you get a stimulated emission and a coherent beam of light is being emitted. Now let us see the construction. A narrow PN junction made from single crystalline gallium arsenide is acting as an active medium. The ends of the junction diode are well polished and made parallel to each other. So it is acting as an optical resonator. There is no external mirrors are being used in this Homo junction. The well polished parallel ends of this junction itself is acting as a mirror. So as a refractive index of gallium arsenide is high, so we need not use any external mirrors for the amplification. The remaining two faces are roughened to eliminate the lacing action in these directions. So next picture, we'll see the PN junction diode, which is forward bias. Now let us see the characteristics of Homo junction. Type: it is a Homo junction semiconductor laser. Active medium, PN junction. Active center, recombination of electrons and holes. Pumping method, direct conversion method. Optical resonator, polished PN junction. Power output, 1 milliwatt power. Nature of output, pulsed or continuous. Output wavelength, 8400 to 8600 angstrom. Let us now see the construction of this Homo junction semiconductor diode laser. It consists of a P region, N region, which is heavily doped, and it is forward biased. That is, P-type material is being connected to the positive of the source, and N-type material is being connected to the negative of the source. And then here, the front and the rear portions are well polished and made parallel, so that the laser action takes place here. So you get the highly monochromatic and coherent beam, whereas the front and the rear are being roughened enough, and other two faces are being roughened enough so that there is no laser action takes place in the other faces. And you have a metal contact at the top and bottom by which external source can be connected. And here the population inversion is achieved by heavily doped P and N regions. In the case of N-type semiconductor, the Fermi level will be just below the conduction band before the N-type and P-type materials are being joined and before doping has been done. Similarly, in the case of P-type, the Fermi level will be just above the valence band. Now, when P and N-type materials are being joined together to form PN junction diode, and by heavy doping, the Fermi level will be pushed inside the conduction band for the N-type, and the Fermi level will be pushed down the valence band of the p-type, and the Fermi level becomes equal for the p and n-type semiconductor. And before biasing, the Fermi level lies within the valence band of the p-type and within the conduction band of the n-type, as shown here in the figure A. When the junction is forward biased with the voltage nearly equal to the bandgap voltage, electrons are started injecting from n-type to the p region, and holes from the p regions are injected into the valence band of the n region, and active region will be found on either side of the p-n junction region. Now let us see this GIF which has been given here. Just carefully look into this movement of electrons and holes. That is when no biasing has been given. You could see that there is a wider depletion region like this. Now you could see now when a biasing has been given, the depletion region has been decreased to a greater extent. Then the crossing of electrons from n-type to p-type, and similarly the holes from p-type to n-type taking place, and electrons combines with the hole to the emission of photons. Now the wavelength emitted will be directly depending on this band gap of the material. Here the band gap of gallium arsenide is 1.44 electrovolt, and then how to find out lambda is equal to hc by Eg. Okay, h nu actually. So when you substitute for nu c by lambda, you get it as hc by Eg. So this is equal to, when you substitute the Planck's constant, c value and band gap value, you end up with 8626 into 10 power minus 10 meter. This is the wavelength emitted in the Homo junction semiconductor material when a gallium arsenide material is used for fabrication. Now let us see the advantages of this Homo junction semiconductor diode laser. It is of low cost, easy to manufacture, high efficiency, powerful and coherent than LED. Arrangement, if you see here, is going to be very simple and compact. It consumes only less power, and the output can be modulated by controlling the junction current. That's all about the advantages. If you see the disadvantages, large threshold current density is required. So every time you have to make the charge carrier stay back in the junction region for the recombination to occur, so which is taking place only in the large current density value. And the output power is only impulsed output. And divergence will be more, poor coherence, okay, and poor electromagnetic field confinement. And the output power is also very low, okay. And when you see the applications, it is almost used in the fiber optic communication system, and it is laser diode is more powerful than LED, so it is preferably used in the fiber optic communication. It is also used in the laser printers, in recording and reading data in CDs and DVDs, barcode reading. It can also be used as a painkiller to heal wounds due to infrared radiation, because it is basically emitted in the infrared region. Now let us see next about this heterojunction semiconductor laser principle. The electron in the conduction band combines with the holes in the valence band and produces energy in the form of heat. This photon induces another electron from the conduction band to move to the valence band and stimulate the emission of coherent photon. Construction. Here, two different materials, one is gallium arsenide and gallium aluminum arsenide is used. If you take gallium arsenide is having the high refractive index. Gallium aluminum arsenide will have a low refractive index. Gallium arsenide will have the low band gap, while gallium aluminum arsenide will have high band gap. Now, a layer of narrow band gap p-type gallium arsenide is sandwiched between the layers of p-type gallium aluminum arsenide, second layer, and n-type gallium aluminum arsenide, fourth layer, which has a wider energy gap and lower refractive index than gallium arsenide. The active region is a gallium arsenide, that is the third layer, where the emission takes place, laser emission takes place. The first layer is a contact layer made up of p-type gallium arsenide, and the fifth layer is a substrate made up of n-type gallium arsenide. So forward biasing is given using the upper and the lower electrode. Now you will understand here. Look into the picture. Here it consisting of five layers, that is 3 P layers and 2 N layers. The first layer is made up of gallium arsenide, second layer is made up of gallium aluminum arsenide, and third layer is made up of gallium arsenide, and the fourth layer is made up of gallium aluminum arsenide, and fifth layer is made up of gallium arsenide. Here, this P-type gallium arsenide will act as an active medium. It is sandwiched in between this gallium aluminum arsenide. One side it is acting as a P-type, other side is acting as an N-type. Now again you can look into this picture. You have a 3 P regions and 2 N region. Again this is also a semiconductor diode laser which is forward bias. So you could see that P layer is being connected to the positive of the source and N layer is being connected to the negative of the source. And again you will not having any optical resonator. The front and the rear region is well polished and it is acting as an optical resonator, whereas the other two ends are roughened enough so that there is no laser action takes place there. A metal contact is made at the top and a bottom layer through which a biasing is being given. Now let us see the characteristics of heterojunction semiconductor laser. Type heterojunction semiconductor laser. Active medium PN junction with various layers. Active center recombination of electrons and holes. Pumping method, direct conversion method. Optical resonator, well polished parallel PN junction itself will act as an optical resonator. No external mirror is being used. Power output is greater than the Homo junction. It is 10 milliwatt power. Here the nature of output is continuous, whereas in Homo junction it was pulsed. Now the output power is 8014 angstrom. Now let us see the construction of this heterojunction semiconductor diode laser. It is consisting of 5 layers. Layer 1, 2, 3, 4 and 5. 1, 2, 3 layers are made up of P-type material and 4 and 5 is made up of N-type material. So still it is a PN junction only. The P-type with the help of metal contact, it is connected to the positive of the battery, and N-type with the metal contact, it is connected to the negative of the battery. It is forward biased. Now if you look into the material used for this fabrication of P and N-type material, first P-type material, first layer is made up of gallium arsenide. The second layer is made up of gallium aluminum arsenide. The third layer, which is considered to be active medium, it is consisting of a gallium arsenide. And the fourth layer is made up of gallium aluminum arsenide. And the fifth layer is made up of a gallium arsenide. It is usually a substrate. Now, you could see here the active region is sandwiched between the gallium aluminum arsenide. The active region is a gallium arsenide, which is sandwiched in between the gallium aluminum arsenide. Let us see the property of this or the features of this gallium arsenide and gallium aluminum arsenide. Gallium arsenide, if you see, they have the less band gap, high refractive index. Whereas gallium aluminum arsenide, if you see, it is having the low refractive index and a high band gap. Okay, so and if you see there, there is no external mirror is being used. The front and the back regions are well polished and made parallel. Gallium arsenide has having a high refractive index. The material which is well polished and made parallel, and this is acting as a active region and this is acting as an optical resonator. Whereas the other, the front and the back regions or top and bottom layers are roughened enough so that the laser action does not take place in these surfaces. Okay, so this property of this two material helps for two confinement. One is a charge carrier confinement, other is a photon confinement. So that is how this heterojunction is made to be having more advantages than the homojunction semiconductor laser. Now the band gap difference of the gallium arsenide and gallium aluminum arsenide, that is the gallium aluminum arsenide is having a more band gap than gallium arsenide. Because of this bandgap difference, it helps in the carrier confinement. Whereas the refractive index of gallium arsenide is greater than the gallium aluminum arsenide. This difference in the refractive index helps for the photon confinement. So in the case of heterojunction, both the carrier and the photon confinement can be made easily because of their fabrication. Now if you look into here, the low bandgap material is sandwiched between the two high bandgap material, so that the charge carriers cannot escape from this active region. It is made to stay back within the active region. So charge carrier confinement takes place. And next is the refractive index difference. The low bandgap material, which is gallium arsenide, will have the high refractive index, whereas the high bandgap gallium aluminum arsenide will have the low refractive index. So one is acting as a denser medium, other is acting as a rarer medium. So when you have the photons are emitted here by the laser action, the photons cannot escape out and it is reflected back to the same medium by total internal reflection, and hence the photon confinement is also taking place easily because of this fabrication of this heterojunction semiconductor laser. So if you see the working principle of this heterojunction is almost the same as a homojunction. When the diode is forward biased, electrons from the fourth layer, and the holes from the second layer are injected into the third layer. The fourth layer is the gallium aluminum arsenide, and second layer is also gallium aluminum arsenide, whereas the third layer, active layer, is a gallium arsenide, thereby creating an active region. Now the population inversion is achieved. Some of the injected charge carriers recombine and produce spontaneously the emitted photons. These photons stimulate the injected charge carriers to emit photons. So these emitted photons are subjected to reflect back and forth at the junction on this highly reflecting material gallium arsenide, and then hence a coherent photon is amplified in the active region, and finally an intense coherent beam of laser emerges out from the PN junction of the active region as shown in the figure. You can see the arrow mark. The arrow mark shows the emission of laser beam from this active region, which is acting as an optical resonator, and the photons get multiplied and you get the highly coherent beam out from this active regions. Now, the bandgap difference prevents the diffusion of injected charge carriers. That is what being told before. Charge carrier confinement is being achieved due to the bandgap difference, and the photon confinement is achieved due to the refractive index difference. Thus, the active region is very narrow. The change in refractive index of the layer is responsible for the confinement of injected charge carriers in the active regions between the layers 3 and 4. Since the active region is very few microns wide, the threshold current density is drastically reduced. Whereas in the case of homojunction, more threshold current density is required, whereas here the threshold current density is drastically reduced. In this type of laser, high power output, narrow spectral with high efficiency and high coherent beam can be achieved, and it is highly stable and has longer life. The wavelength of the light emitted by this is 8014 angstrom. That is, the bandgap of gallium aluminum arsenide is 1.55 electrovolt. When you substitute back into the formula, knowing the value of Planck's constant and C, you get the value to be 8014 into 10 power minus 10 meter. Thank you for watching.